Today, let's talk about the force on moving charged particle in magnetic field. When a positive charged particle moves to a magnetic field, a force on the particle can occur. For this case, an upward force acted on a particle as it encounters magnetic field. This force is called magnetic force and denoted as symbol FB. So here is the region of magnetic field. X means the direction is into the pitch. So once the particle enters the magnetic field, it will deflect. The magnetic force is the one that caused the particle to deflect. Just now, we look at the deflection of the positive charge particle. Where do you think will be the deflection path if the charge is negative? So now, we put the negative sign to make the charge negative. You will see that the charge will be deflected downwards due to the magnetic force that is in opposite direction to that on a positive charge. Let's say if we increase the magnitude of the negative charge, the particle will deflect more. The particle is actually moving in circular motion once it enters the magnetic field. So by looking at the size of the circular path, increasing the magnitude of charge also shows that the magnetic force is getting stronger. So we can conclude that if you increase the magnitude of charge, your magnetic force on the particle will become stronger. Now, let's investigate the effect of direction and strength of magnetic field on the deflection. We go back to the positive charge particle with a charge of positive 1.6 exponent negative 19 coulomb. Then, we change the direction of the magnetic field to out of the pitch. Deflection will change. As you can see here, the deflection will be going down. Then we try to add the strength of the magnetic field. Let's make it around 0.8 Tesla. Notice again, as we increase the strength of the field, the particle will deflect more. That means bigger force acting on the particle as the strength of the magnetic field increases. We have discussed the two factors that influence the magnetic force that are charge of particle and the magnetic field strength. The equation for magnetic force on a charged particle in the magnetic field is given by F equals to Q and the cross product between V and B. Q is the charge of particle in coulomb, V is the velocity of particle in SI unit ms-1, and B is the strength of the magnetic field in Tesla. This formula is equivalent to QVB sine theta, where theta is the angle between V and B. So in order for an object to experience magnetic force, it has to be charged and move in magnetic field. So the two factors that we did not explore were velocity and sine theta. The velocity of the particle is directly proportional to the magnetic force. So the faster the particle moves, the stronger force needed to push the particle in circular path. And for every animation we saw just now, the angle is always 90 degrees. So sine 90 is equals to 1. However, imagine we had magnet arranged like this, and the charged particle is traveling along the same direction as the field strength. For this situation, the angle between V and B is 0. The V and B vectors are parallel to each other, so the angle is 0, and the sine of 0 is 0. So in this situation, there will be no magnetic force. We already know that the charged particle will deflect in circular path as it encounters magnetic field. The question is, can we predict the direction of the deflection? Can we know the direction of the magnetic force acting on the charged particle? It's important to know that the magnetic force acting on the charged particle is 90 degrees to the velocity of the particle. So as you can see in this diagram, if the particle is heading in this direction, so you will see that the force here is 90 degrees to its velocity. We can actually predict the direction of the magnetic force or velocity or magnetic field by using a rule known as right-hand rule for moving charges in magnetic field. So here how it works. Hold your hand open, point your thumb 90 degrees to the fingers. Your thumb will be pointing to the direction of force, and the direction of the magnetic field follows the direction of the palm facing. So your palm now showing that the B is out of the pitch, same like this situation. And then your fingers will show the direction of velocity for positive charge. So this rule is applied specifically for positively charged particle. You can also curl your fingers naturally like this diagram. Curl your fingers naturally to vector B to show the cross product relation between V and B. Let's see this situation. A positive charge particle is moving to the right and the direction of magnetic field is into the page. This red arrow here shows the direction of velocity. To check the direction of the magnetic force at this point, open your right hand like this, point your fingers in the direction of velocity, and then you have to point your palm in the direction of magnetic field. So for this case, magnetic field is into the page, so you have to turn your hand so that your palm is facing into the page. Like this. And your thumb will show the direction of upward magnetic force. So this black arrow here shows the direction of magnetic force. So that is why you can see that the charged particle is continue to deflect upward. Now, let's check the direction of magnetic force at this point. As usual, fingers follow the direction of the red arrow, which is the velocity. Then your thumb will show the magnetic force 90 degrees to the fingers. The charged particle will continue to deflect because it is pushed by the magnetic force, and it will make a circular path as long as there is magnetic field. What if the charge is negative? Notice, for a negative charge, it deflects in opposite direction. Thus, right-hand rule applicable for negative charge. So here how it works. For a negative charge particle, the force is opposite to the direction of the thumb. So, this is the direction of the force for positive charge particle. Then, for the negative particle, it will be opposite to that determined by right-hand rule. This is a demonstration of a cathode ray tube. It produces a beam of electrons. The blue lines represent the fast electron moving to the left. Let's check the magnetic force acting on the electrons in the case of magnetic field points in this direction. So, the velocity in this way, the magnetic field is in this way. By using right-hand rule curling method, the force should be up. However, we'll see that the force is not up, it's down. As I told previously, the force on electron should opposite to the direction on positive charge determined by right-hand rule. So the electrons will be deflected downwards. Lastly, let's imagine this situation. For a magnet that is facing towards each other, and here is the positive charge particle and it's moving down. You will see that by using right-hand rule, the magnetic force will be out of the page. So, please try yourself to get the correct orientation for right-hand rule.